All right, so one of the things we found out in Lab 6 was that sometimes we care about more things than just injectivity and surjectivity. Sometimes we care about whether or not we could, there are certain objects, vectors that will be outputs that we have as 0, or things that are invisible to our transformation. And we also want to sometimes know if we can, what objects we should expect to see as a result of our transformation. So this is in the kind of two main types of transformation spaces. So vector spaces that are related specifically to our transformation. The first is the idea of null space, and this will be kind of our way of looking at invisible objects. So definition time. The null space of a linear transformation going from a domain V to a codomain W is the subset of V that maps to W. That is to say, the null space for a transformation T is the set of all vectors in the domain such that their transformation becomes 0. You think of this as just being the inputs that get mapped to 0. Now, in other places, you may find this referred to as the kernel of T or ker T. We're just going to call it the null space of T. We say that the nullity of a linear transformation is the dimension of the subspace null of T. So in order to find our null space, we need or our nullity, we need to first find a basis for the null space, and then to just count how many vectors we have in it. So here's the main idea. We've got some sort of domain V that we're looking at, and we have our codomain W, and what we want to do is we want to take and go from our domain to our codomain. However, there's this whole part of our domain, the null space for T, that if I take any vector in here and I map to the codomain, I'm going to immediately go to whatever the 0 vector is for that. And so we want to figure out what portion of our domain contains this null space. Let's go through an example. Let's say we had a domain V of ax squared plus 2bx plus b, and we wanted to go from V P1 by taking vectors in V and sending them to 2ax plus 2b. We want to find the null space for this. So the null space for this f, this function f, is going to be the set of all vectors in our domain such that their transformation equals 0. So we have then the set of all ax squared plus 2bx plus b, so that's what things look like in our domain, such that their function value of ax squared plus 2bx plus b, which is just 2ax plus 2b, equals 0. So, right, so we want to look at this equation and figure out what this means for our potential vectors that we have. So if we look at this equation and we compare our coefficients, we end up getting the system of equations 2a equals 0 and 2b equals 0. So what this tells us is that a has to be 0 and b has to be 0. So what we really have is the set of all ax squared plus 2bx plus b such that b a equals 0 and b equals 0. And so really what we have is just the 0 vector. So sometimes this will happen, right? Sometimes we'll have a transformation where the only way we should get an output of 0 is if we put in 0 as our input. So since this happens, we just have the 0 vector. So notice that this is not a basis, right? Because we just have the linearly independent vector, or we just have the spanning vector, but we don't have something that's linearly independent because 0 can't be linearly independent. So in this example, our nullity would be 0 because there's no elements in the basis for the null space, and we say then that F has a trivial null space. In other words, it only has the 0 vector as a potential thing that will map to 0. So let's maybe try a different example so we can see a little bit more of what's going on. And maybe something that doesn't go from a crazy subspace, something that just kind of goes from something normal to something less, or also pretty normal. So we want to go ahead and define our function f going from 2 by 2 matrices to R4 by taking some input A, B, C, D and going to A, B plus A, B, C as an output. So we want to know which things are going to get mapped to 0. So the null space for this function is going to be the set of all vectors in M2 by 2 such that f of that vector equals zeros. So here, the reason it's this zeros is we have vectors in R4 as output, and so we're going to define 0 this way. So we're really looking at the set of all A, B, C, D Okay, so using this, then, we'll get a system of equations that says A equals 0, B plus A equals 0, B equals 0, and C equals 0. There's not really anything to solve for here, because if we have A is 0 and B is 0, and then B plus A is definitely 0, and we don't have to worry at all about having no solution or anything weird happening. And so here we just have the set of all A, B, C, D such that A equals 0, B equals 0, and C equals 0. But D didn't have any restrictions, so it can be anything in the real numbers. So then this is just going to become the set of all 0, 0, 0, D such that D is a real number. And so here we can check that we have then the span of 0, 0, 0, 1. And so, first of all, does this span? The answer is yes. Second question, is it linearly independent? Is the set containing 0, 0, 0, 1 linearly independent? Well, it has only one vector, and that vector isn't the 0 vector, so it will indeed be linearly independent. So it's a basis, which is great. So the null space for F is going to be the span of 0, 0, 0, 1. So just to kind of help denote the difference, this is the null space is the span of that vector. However, the basis for the null space of F is just the set containing 0, 0, 0, 1. So there's only one vector in here. And so that means that the nullity is going to be 1 because there is one element for the basis of the null space. Also notice that because there's more than one element of the null space, f of 0, 0, 0, 1, which is the same as f of 0, 0, 0, 2, is going to be equal to the 0 vector. But we have two different inputs that map to the same output. So that means that f is not going to be 1 to 1 or injective. Interesting. So what that tells us then is that we have something that has a nullity that is 1 or more, basically not 0, then we can't have an injective function. So this kind of relates to our stuff from last week. All right, so notice that all the things we've used above, we didn't check if they were linear transformations, but they are linear transformations. So if you want to get a little bit of extra practice with linear transformations, you can go verify that those things are linear transformations, and it'll help that you kind of know the result. And if you're still having trouble trying to show something is a linear transformation, or you think it's not for some reason, let me know. I'm more than happy to chat about it. All right, so the name null space is kind of implying that this set is a vector space. And we're going to end up giving this a kind of a formal definition with this theorem. So given vector spaces V and W in a linear transformation, the null space, null of T, is going to be a subspace of the domain. So the subspace of V, this is just the domain. There's a short little proof here that justifies why it's a subspace, but this is something that's kind of just splitting hairs at this point. So I'm going to go ahead and skip that explanation, but it's there to read if you'd like. Now, we also can have a null space for a matrix. So we talked about how linear transformations can be represented as matrices. And so if we wanted to go ahead and find a null space for a matrix, that is also something we can do. So the null space, or null of an m by n matrix, is the null space of the corresponding transformation. So in other words, what we're saying is the null space for M is going to be the set of all X that could be inputs. So here, since it's an M by N matrix, they're going to be an Rn, such that M times X is the zero vector. And here, when I just say write the zero, I'm talking about the zero vector in Rm, the properly sized zero vector for whatever we need. All right, so given this matrix, we want to go ahead and find the null space for the matrix. So the null space for M is going to be the set of all X in R3, because it has 3 columns, such that M times X is going to be equal to the zero vector for the correct space. So what that's saying is we have the set of all ABC such that our matrix times ABC gives us an output of the zero vector. And so this is something that we've actually solved below here. So we've got this initial setup, we put the matrix, we augment with the zeros because that's how we solve for these A, B's, and C's. And then we get the reduced row echelon form. And here what we get as equations are that A minus 2C equals 0, B plus 3C equals 0. C is a free variable because it doesn't have a leading term. And so what we get is A equals 2C, B equals negative 3C, and once again, C is a free variable. It's in the real numbers. And so we can use this to rewrite our set to be the set of all A, B, C such that A equals 2C, B equals negative 3C. So this is the set of 2C, negative 3C, C, such that C is a real number. And so this is just going to be the span of the vector 2, negative 3, 1. So we can check, we can verify that this is linearly independent, but there's only one set. And so the null space for M, write it down here, is just the span of this vector, 2, negative 3, 1. And so here, if we were asked the nullity of this matrix, is going to be 1, because we have one linearly independent vector there in our basis. Okay, so that's going to be our idea for null space. We also have the idea of having what's known as a range space. So we also want to know which things we could possibly get out as outputs. So when we're looking at this, with most functions, we have kind of a set that we have objects coming from, which is our domain. And we often will refer to it as the domain space in linear algebra. But we also want to be looking at the codomain. So we say that the codomain of a linear transformation is the vector space to which we map. And so when we're saying we're going from V to W, the set W is our codomain. And so in our previous examples, our codomains were P1 and R4. The codomain tends to be much more interesting than the set of all the things that we are that get mapped to. Often not every vector in the codomain gets mapped to, and if they did, we would say that our transformation was onto. Right? So what we're going to have instead is this idea of the range space. So we say that the range space of a linear transformation is the subspace of the codomain that contains all elements from the all the outputs from V under the transformation. So our formal definition is going to say that the range space for T is the set of all T of V such that V is an element of the domain. So this is the set of all possible outputs. So to kind of continue the bit of visualization here, we had talked about the domain. And we have this idea of the null space of our transformation. We have our codomain. And there's going to be a set here that gets mapped to in the codomain, and we're going to call this the range of the transformation. And so here in the range, we're going to have that 0 vector. We should always get that 0 vector. And our null space is going to go ahead straight to the 0 vector. But the domain only have things go somewhere into the range. You'll never see it outside of our function T shoot anything outside of the range. So what we're interested in is in this range space. There also will be the idea of rank. So we say that the rank of a transformation is the dimension of the range space. So to find the rank, similar to how we found the nullity, is we need to first find a basis for the range space, and then we need to count the number of vectors. All right, so similar to before, if we have a transformation going from V to W, then the range space is going to be a subspace of the codomain, meaning that it is a vector space. Okay, so let's go ahead and walk through trying to find the range space for a function. So we want to show for this function, so this is the function we were dealing with before, if we want the range space of this function, that's the set of all outputs such that the input is from the vector space, and so this is going to be the set of all f of ax squared plus 2bx plus b such that a and b are in the real numbers. And so this is just going to be the set of all 2ax plus 2b such that a and b are real numbers. Well, we don't have any conditions, so we can write this as a spanning set. All right, so this is the span of 2x and 2. So it spans. We also need to show that it's linearly independent. So linearly independent. So if we have alpha 1 times 2x plus alpha 2 times 2 We set that equal to 0. Looking at our coefficients, what that tells us is that 2 alpha 1 equals 0 and 2 alpha 2 equals 0, which tells us that alpha 1 and alpha 2 both have to be 0. So we have a set that's linearly independent, and it's a spanning set. Now, we want to show that it spans P2, or if we want to show it spans P1, what we have to do is we have to set this linear combination equal to AX plus B, and then we would go ahead and verify that we got at least one solution. You can do that on your own if you'd like, and so indeed this will end up being P1. So note that we have a basis here. So the rank of this function is going to be 2. And in fact, what this ends up meaning, since the range is equal to the codomain, that we have an onto mapping, or a surjective mapping. All right, so let's look back at our other function. Let's say now we want to go ahead and look at this function we had before, going from M2 by 2 to R4. And we wanted to find the range space and the rank for this function. So the range space of the function is the set of all f of v such that v is a vector in M2 by 2. And so we have then the set of all f of a, b, c, d such that a, b, c, and d are part of the real numbers. Although in the end this d is not going to be necessary because it's not included as part of our output. So what we really have is the set of all a, b plus a, b, and c such that a, b, and c are in the real numbers. And so again, we don't have any restrictions at this point, so we're allowed to say that we have a spanning set. So span of 1, 1, 0, 0, 0, 1, 1, 0, and 0, 0, 0, 1. So as a spanning set, we would need to check basis. So check linear independence on own. It will just kind of give you a little bit of a spoiler alert and tell you that this one is indeed linearly independent. And so we have a basis. We have this as our range space of F. And so notice that then the rank of a function f is going to equal 3. Then we can compare that to the dimension of the codomain, which is just the dimension of R4, which is 4. And so notice here that we do not have a rank equal to our dimension of our codomain this time. That will come up a little bit in the future. Here our codomain is R4, and the range space was not equal to our codomain. So what that means is that we don't have every element in R4 mapped to by our function. So that means we're not onto. Okay, so similar to how we had the null space for a matrix, we're also going to be able to have the range space for a matrix. And sometimes this is going to be called the column space for a matrix. So given a matrix that's m by n, the range space for the matrix is going to be the set of all m times v, where v is an element of Rn. Right, so the idea is it's just all the possible matrix outputs that we could get. All right, so to find our column space, we want to find all of the vectors that are possible as outputs for our basis. And so there's actually a process for us to get this very quickly. So our process for finding a basis for the column space of matrix is first to use elementary row operations to get the matrix in reduced row echelon form. After that, we can identify the columns that have pivots, and the basis for the column space is going to be the span of the columns in the original matrix associated with those pivot columns. So if we had our matrix here that we started off with, and we want to determine the range space for it, what we do is we'll first get it into reduced row echelon form. Now, once we've gotten it into, I don't know why this is here, this shouldn't be. Once we've gotten it into reduced row echelon form, we're going to look for our columns with our pivots. So our leading ones, and whatever the columns were in the original matrix are the columns that we get to use in order to create our basis for our column space. So our column space for this matrix is going to be the span of 1, 2, -1, and 1, 1, 0. We also could go ahead and show this a little bit more spelled out by augmenting on the possible outputs we could get. And so we augment this on, and so what we get here is that this will be issue for potentially no solution. So in order to have a solution, this needs to be 0. Needs to be 0 in order for it to be a potential output of ours. So that means our range space for our matrix is going to equal set of all A, B, C, such that -A plus B plus C equals 0. And so we could rewrite this to instead say A equals B plus C. And so what we'll get then is the set of all B plus C, B, C, such that B and C are real numbers. And this will be the span of 1, 1, 0 and 1, 0, 1. So you might notice that this is a different spanning set than the one we had before. But what you should notice is that they still will span the exact same space. Now you can show that those two span the same space by setting their linear combinations equal to each other. And what you also might notice is that if you take 2 times this vector minus 1 times this vector, you'll get this vector, and this one's already there. You still would need to show linear independence, but we'll notice from both of these that they have the same number of linearly independent vectors, and so our rank for our matrix is going to be 2. Alright, so we want to talk about how this is going to actually relate to our ideas for injectivity and surjectivity. So let's consider this discussion from the point of view of radiography. We saw that some of our transformations had the property where 2 objects could give the same radiograph. In particular, this particular radiographic transformation would not be 1-to-1. Right, because if 2 different objects giving the same radiograph, that's our definition for not being 1-to-1. Furthermore, we found 2 objects to give us the same radiograph. Their difference would be invisible. What that means is that the difference is in the null space of the radiographic transformation. So if we had an object that is invisible to the radiographic transformation, any scalar multiple of it is also going to be invisible. That means that more than one radiographic object is invisible, which is going to produce the same radiograph, which is 0, which means we can't have an injective transformation. Now we say, we've got a theorem here, and it says that a linear transformation is injective if and only if the null space for that transformation is just equal to the 0 vector. So remember, injective, same as 1 to 1. And there's a nice little proof of it. Again, I know this is a class mostly taken by computer scientists, less by math people. So if you are a math person who's interested, go through the proof. I'd be happy to talk about it with you. But I'm going to skip it for now. So what we have then, based on this theorem, is a process to determine injectivity. So the question is the null space equal to the 0 vector? Or in other words, is the nullity equal to 0? If yes, then we have 1 to 1. If no, then we have that it's not 1 to 1. We also found that there are radiographs that could not be produced from an object given a certain radiographic transformation. This means that there's a radiograph in the codomain that is not mapped to from the domain. If this happens, then the radiographic transformation is not onto. So, given vector spaces V and W, and a transformation going from V to W, transformation is going to be called surjective or onto if and only if the range space for the transformation is equal to the codomain. Furthermore, what this means is that the rank for the transformation is going to be equal to the dimension of the codomain. And so that's a thing we'll need if we want to be able to get a surjective transformation. So we can combine these results to say that a transformation going from V to the range space of T, which would need to be equal to the codomain in order for this to be a bijection, is going to be a bijection if and only if the null space for the transformation is equal to 0. So let's say we had a transformation going from V to P1 from earlier. We want to determine that V is isomorphic to P1. So what we mean by isomorphic, so this is the word isomorphic. And just a reminder, it means the idea there is a bijection between these spaces. So we want to go ahead and show that we have a bijection. So from our earlier example, so example 8.1 showed us that the nullity of this transformation was 0, which tells us that the transformation is 1 to 1. And example 8.4 told us that the dimension of our codomain and the rank of our transformation were the same. They were equal, which tells us that F is onto. So combined these two things, our transformation is a bijection. which tells us that our vector space V is isomorphic to P1. It's cool. We've used the information we had to combine and get something that is isomorphic. Now we can go ahead and check whether or not the other transformation we looked at is going to be injective and surjective. So using these examples that we had from before, example 8.2 told us that the nullity of our transformation was equal to 1, which means it's not equal to 0. And from our theorem, what that tells us is that f is not 1 to 1. Okay, so that answers the 1 to 1 question. Now we look back at example 8.5, what we were told is that the rank is 3, but the dimension of the codomain was 4. So since these are not equal, f is not onto either. Alright, so these ideas of rank and nullity and the dimension of the null space and the column space lead us to a really interesting and useful theorem known as the rank nullity theorem. So these last couple of examples have kind of illustrated this a little bit. Maybe you picked up on this, maybe you haven't. But the rank nullity theorem says that if we have V and W are vector spaces and the transformation goes from V to W is a linear transformation, then the dimension of the domain has to equal the rank plus the nullity. Essentially, you have your domain split up into vectors that go to 0 and vectors that don't go to 0. And so the nullity talks about the vectors that go to 0, and this kind of builds up the space, and the rank tells us about the vectors that don't go to 0, which helps us build our range. So there's a very long, drawn-out proof for all of this. And one of the nice things is that this theorem says that we can separate our basis into the things that map to 0 and things that map to other things. And so this gives us a nice other result that we can use. So let V and W be vector spaces and T going from V to W be a linear transformation. If we have a basis for the domain, and then what we're saying is that we can transform each of our domain vectors to form a basis for our range space in order for us to get the range of T. So the rank nullity theorem is going to be useful for us to determine whether or not very quickly we can have something that's 1 to 1. So let's say we had a transformation going from M2 by 5 to P4. So the dimension of M2 by 5, which is the dimension of the domain, is 10, whereas the dimension of P4, which is the dimension of the codomain, is going to be equal to 5. So we want to see if we can use this rank nullity theorem to determine that the transformation could never be 1 to 1. So what we'll do is we'll make an assumption. If T were 1 to 1, the nullity of T would be 0. And if it was 0, then based on the rank nullity theorem, the dimension of the domain would have to be equal to the rank plus the nullity. And if we're assuming that this is 0, what that tells us is that 10 would have to equal the rank plus 0, which means that the rank is 10. However, the rank has to be less than or equal to the dimension of the codomain. But this is not the case, since 10 is not less than or equal to 5. So we have a contradiction. So since we have a contradiction, that means the thing we assumed originally is wrong. So t cannot be 1-to-1. So we tried to make it 1-to-1. Notice that we didn't need to know anything about the transformation itself. We just need to know about the dimension of the domain and the dimension of the codomain. So this can be kind of a quick check to see if it's possible. Note that this is not a proof that it definitely will happen. But if you get this, then you should be able to at least narrow down whether or not you can get something 1-to-1 or not. And if you can, then you can go ahead and not worry about it. And if you can, then you still have to prove that it's injective or surjective by going through the steps. All right, so there's one other example from this section on the next page, on page 126. It is for you to read and kind of give you guys a little bit of extra example just in case you want to look at it. Once you do, if you understand it, great. If you don't, ask about it in the comments. And then the next thing that you'll see in the next video is a chance to work on the ice. So we'll be looking at ice 7 in the next video. So if you haven't had a chance, well, you probably haven't had a chance, you're watching this video. So once you're done watching this, give ice 7 a try and then come and watch the next video after you've given it a good shot.